Hi everyone, in this video we are going to look at the next section, 8.2, distribution of the sample proportion. And in this section we get away from talking means and standard deviations, and instead we kind of shift our focus on proportions, which we haven't talked too much about yet, but we get introduced to here. It starts out with a little quick example. If 65 out of 100 households favor the new school budget, we could write that as a proportion. So this is just telling you what a proportion is. We could write that 65 out of 100 as a fraction or a decimal, 0.65, or a percent, 65%. And you've done that before, but those are examples of proportions. This to that, 65 out of 100. And in dealing with proportions and sample data and all that, it's rare to have access to a total population, so we typically obtain estimates as we do with means and standard deviations. That comes from sample data. With proportions, we're going to be dealing with sample data and sample estimates of population parameters such as p. All right, so the kind of formally stating our proportion here, suppose a random sample of little n is obtained from a population in which each individual either does or does not have some characteristic. So in the example above, it's being in favor of a new school budget. And then we define the sample proportion with a caret over the p, so we read it as p hat equals x over n. N is the sample size, x is the number in the with the characteristic, so the number in favor of the school budget. So that's our formula, if you will, for sample proportion. Of quick examples, if you want to read through them, pause the video. The first one, though, we have 150 that said, yes, I am on a low-carb diet out of 1,000 in the population. So we write that as p hat equals x 150 over n 1,000. That is 0.15 or 15%. And then in the second example, 349 responded yes to the question. 349, and then the sample size was 1,745. And so our sample proportion, our p hat in that one is 0.20, 20%. Okay, now in this next example, we're going to do something where, again, I would have done this in Minitab if it were class, but I'll kind of walk you through the process of what this looks like through this example. So we're given the statement that 76% of Americans believe that the state of moral values in the U.S. is getting worse, and then we are going to create, using Minitab, what is a sampling proportion, much like, so we're going to tie into the work that we did in the last section to create a sampling proportion for samples of size 10, and then 25, and then 60. Okay, so what does that mean? I use Minitab to create random data, and these columns are all labeled Bernoulli's. And what this test does in Minitab is it spits out a bunch of ones and zeros, and the one would be having the characteristic, so believing that moral values are getting worse, and 0 would be not having the characteristic, and it's they don't think that the morals are getting worse in this country. Okay, and also in doing this, in running this simulation in Minitab, we can tell Minitab, well, there's a 76% chance that you spit out a 1. And that's why, looking across row 1, we see, if you count them up, you have 7 ones out of 10 in your sample, so the p hat for that sample is 0.7. In sample 2, the p hat is 0.7 because there's a 76, so most of the time it's going to spit out a 1. 75% of the time it spits out a 1. Every once in a while you get a 0. So it is possible to get 80% of the sample. It's possible to get 100% of the sample because it's such a high setting to have it at 76%. Okay, and this is equivalent to finding groups of 10 people, well, random samples of 10 people, and asking them all that question and recording that data. Just Minitab allows us to run that simulation 1,000 times with the click of a button. Okay, we see down here we have a 0.6, we have a 0.6. I don't see any 0.5s. It's possible, but less likely to have something that low when there's a 76% chance of putting a 1 there, of someone saying yes to the answer to that question. Okay, and now moving down a little bit here, we create these distributions. So I generate 1,000 rows of data, and what I'm looking at in the leftmost histogram here is in A, I have that sampling proportion. So what percent of the time was a zero point 0.7 spit out? According to this one, 25% of the time. What percent of the time was a 0.8 spit out? How often did I get 100%? Did I ever get a 40%? Did I ever get a 30%? And what we see is we get a distribution that kind of fits under that bell curve. Not perfectly, but it looks pretty good. And then if I increase my sample size in the next distribution, so that would be generating 25 rows of data. All right, and then finding the p hat for those 25 people in the group, we get a histogram that looks much more normal. See how it fits under that bell curve much better. Doesn't look quite as skewed. This one looked a little skewed to the left. This one maybe a little bit, but less so. And then if I increase that sample size to 60, make it even higher, well, then I'm definitely looking very normal. And what do we know about our normal distribution? We have this giant table of numbers that we can apply and answer questions about what is the probability that blank, or what proportion of the population blank, okay? So that's what we can then do with this, right? There's a mean and a standard deviation in there too, right? If I look at the center of my distribution, and it's even easier to see. So let me move this down a little bit. There we go. The shape, first, we can see it becomes normal as the sample size increases. The center, the mean of this distribution, so I know we're talking about proportions here, but my distribution has a center, a mean, and if I draw my midline down here, it looks like it's between 0.7 and 0.8. I'm going to go ahead and say it's a pretty good bet that it's at 0.76, that percent from the beginning of this problem. And then the standard deviation, as your sample size increases, the standard deviation of that sampling distribution decreases. And the standard deviation is how far away, if I go and look at the inflection points on my bell curve, about there and about there. So we can have a mean and a standard deviation generated from a problem that's talking about proportions. And now we get to the slide that's got all the formulas, the main idea contained within the section. It's called the sampling distribution of p hat. For a simple random sample of size n with a population proportion p, the sampling distribution of p hat is approximately normal, provided that this is true. So this formula is the test, and we're not going to go into really where this formula comes from, but it's the test for is the distribution normal. If my n, sample size, times p, the proportion, times 1 minus p, is greater than or equal to 10, then that means that my distribution is approximately normal. So that's what that is a check for. Then the mean of the distribution, and my spacing is off a little bit here, but the mean of my sampling distribution is the proportion that we're given, that we're talking about in the problem. The standard deviation, here's a formula that, again, we're not going to get into where this formula comes from, but this is how we can compute the standard deviation for the sampling distribution, right? You can kind of see it on the bell curve that, how far away one standard deviation would be. That's the formula of how we officially compute it. And then the other thing that we kind of have to check for is, are our samples independent of each other? It's just an additional step, an additional check. Is little n, the sample size, less than 5% of big N, right? It would be unreasonable to take a sample of 1,000 SUNY Broome students, right? That's a really, really big sample, right? So that way, if someone were to recreate the experiment, right, there might be students that are within both samples. So when you're doing real statistics, you have to check and verify that these things are true, or else you're not doing good statistics. All right, now let's look at an example using those formulas, and we change our 76% to 82%. I'm not sure exactly why, but we use a different number here. So we have 82%, remember that number, of Americans believe that, again, the state of moral values is getting worse, and we're taking a random sample of 80 Americans. Describe the sampling distribution, okay? So first thing that we're going to do is verify our two pieces that we have to check off. Is my sample size less than 5% of the population? So is little n less than or equal to 0.05 times big N? Well, little n is 80, And capital N, you look to the problem to kind of figure out what the population is, and it's the second word there, 82% of Americans. Anybody know the population of America? I mean, you could look it up pretty quickly, but it's like 300-ish million. I don't know. It might even be 340 million. And that is very quickly checked off. And so I'm just going to make a check mark without even typing that in my calculator. 0.05 times 300 million is still pretty darn big. Okay, so that checks that our sample size is less than 5% of our population. Then we take n times p times 1 minus p. So n is my sample size, 80. P is the proportion in the problem, 82%, 0.82. And then 1 minus 0.82. Is that bigger than 10? And it is. So when you type that in your calculator, you get 11.808, which is bigger than 10. So we say check. And that means we are approximately normal. That is the shape of our distribution. All right. Then we come and compute these two other pieces, the center and the spread. And let me label this, squeeze it in a little bit. This is the center of the distribution, and then standard deviation is the spread of the distribution. So mu subscript p hat, the mean of the sampling distribution, is 0.82, 82%. And the standard deviation of the sampling distribution is a big old square root. P is 0.82. We've used it a couple times now. 1 minus P, 1 minus 0.82, divided by, again, the sample size is 80. So when you type that into your calculator, you should get 0.043. 0.043, or even 4%. 0.04 would be good too. And that is our standard deviation. And these standard deviations are always going to be small, because your mean is small, right? The mean that I got first was 82%, 0.82, and the standard deviation is 4%. Okay, so those should always be pretty small numbers. A note about typing this into your calculator: you can do it all in one step. My suggestion would be to have the 1 minus 0.82, oops, I need to highlight that, to have the 1 minus 0.82 part done ahead of time. Like, that's fairly quick to subtract, 0.18. So I just typed into my calculator the square root, this number times this number divided by that number. Otherwise, you need that set of parentheses around the 1 minus 0.82, which is fine. It's just it's a little bit less to think about when you're entering all that into your calculator. Okay, so that is it for that problem. That's all there. Okay, in this next example, we are given the information that according to creditcard.com, 29% of adults do not have a credit card. All right, and then we're basing the rest of the work off of that known percentage. All right, and in part A, we are given that we're surveying 500 adults, asking them whether they have a credit card. Describe the sampling distribution of p hat. So what that means when you see describe the sampling distribution, what is the shape, what is the center, what is the spread? Okay, the center is the mean of p hat, the spread is the standard deviation of p hat, and the shape is hopefully normal, but I'm not going to write that down. First, we have to verify that little n is less than 5% of big N, and n times p times 1 minus p is greater than or equal to 10. Okay, we verify those two pieces, and then we know the shape is normal. So let's check that. The first one, sample size is 500, is less than or equal to 0.05 times, what is my capital N? Survey 500 adults. So we need the population of adults, which is still in the hundreds of millions. So you can kind of infer that, yes, that's going to be checked off. We're okay there. Right? You don't always have to compute that, but you do have to consider it for a minute. And then we verify that little n, 500, times p, which is 29%, 0.29, that's the given percentage, times 1 minus p, greater than or equal to 10. Hopefully it is. Check it in your calculator. That should just be a 10 there. So let me type this in here. 500 times 0.29 times 1 minus 0.29 is 102.95, which is greater than or equal to 10. Check. So what does that mean? The shape of the distribution is approximately normal. I can use Table 5 and apply all the stuff in Table 5 to this problem. Now the center of my distribution, mu, is 29% p. This is our p up here. I didn't write that down. I probably should have. That is the p, the percentage, the proportion. All right, and then the spread, the standard deviation, that's that big formula, the square root of p, 0.29, times 1 minus p, divided by 500. When you type that into your calculator, you get 0.020. So I'm 0202 after that. So yeah, we'll just leave it at 0.02 actually. So this is equal to 0.02. I'm just going to take the first two decimal places. It'll make it a little bit neater when I write out the rest. Okay, so that is it for Part A. And now Part A doesn't ask for this, but I'm going to do a little bit above and beyond. And I want to draw my distribution. Whoops, let's drag the screen up. There we go. I want to draw this distribution. All right, so what does this look like? Well, let me draw a horizontal line. Because of the shape being approximately normal, I can draw my nice looking bell curve there. The center of the distribution, 0.29. And the spread, the standard deviation, I can subtract 0.02 and add 0.02, 0.31. I can subtract it and add it again, 0.25, 0.33, etc. And I could write one more on there. I'll just write 2 for right now. All right, that is what this distribution looks like. Now, we get to Part B. What is the probability that in a sample of 500 adults, more than 30% do not have a cell phone, or a credit card, excuse me. So I want, and I'm going to write this in that formal way, the probability that x is greater than 0.30. Now, let's take a look at what that looks like on our distribution, and I'm just going to shade it for a minute and then kind of erase it because we're going to draw it on it with other problems also. So here's about where, oh, actually, no, it would be in the middle. Here's about where 30% would be. And what's the probability that we are to the right of that? Well, that's one where I have to go and look up something on the table and then subtract from 1, right? When we're looking to the right of a z-score, we subtract from 1. So this is equal to 1 minus the probability that x is less than 30%, 0.30. So how do I do that, though? In order to use my z-table, I have to have a z-score. So that's what we have to do next year. We want to go and compute z equals x minus mu over sigma. Looks a little bit different in this section. Z actually is going to equal p hat minus mu of the sampling distribution over sigma of the sampling distribution. So it's the same idea behind the formula. We write it specific to the things that we're talking about in this section. So p hat is the 0.30 minus mu, the mean, 0.29, over sigma, the standard deviation, 0.02. Type that into your calculator. Should get a half. You should get 0.5. So now I can go back to my work up here. I want 1 minus what is the probability that z is less than 1/2 or 0.5. Actually, I'm going to write 0.5. 0.50. Now I can look this up on table 5. If you do look that up on table 5, and I encourage you to practice using that table, you get 1 minus 0.6915. Is what you get when you look that up on table 5. And then finally do this subtraction, and you get 0.3085. Or we can say that's approximately 31%. So let me scroll back up for a minute to the wording of this part B here. What's the probability that in a sample of 500 adults, more than 30% don't have a credit card? I know I read that quick, but you can pause and read it, right? There is a 31% chance that if you have a group of 500 adults, more than 30% don't have a credit card. I think for this problem, to keep this a little bit shorter because the last section was a little bit longer, I'm going to skip part C. I'll just mention something about it, and then we'll do part D. For part C, what is the probability that between 25% and 30% do not have one? Right. Well, now I'm looking here, 25%, here, 30%. What's the probability that we're between those two percentages? This is one where you compute a z-score and another z-score, one for 25, one for 30. You find two areas, and then you subtract those two areas. We saw that in the last section. We see it again in this section. And then finally, part D, where it says, would it be unusual for a random sample of 500 adults to result in 125 or fewer, emphasize that, who do not have one? In part D, I'm not given a percent, which is different than it was in B, but that's no big deal. We can find that percent and then shade it on our distribution. So let's do that. So I'm going to let's go down here for part D. We'll change color here, throw green at you. Part D. First, I need to find the p-hat in this problem because I was only given 125 out of 500 people. So we just have that like one extra step in this part of the problem, and that's 25%, 0.25. So now we can say, all right, what is the probability that p-hat is less than 0.25? And actually, up in the earlier problem where I wrote x, I should have written p-hat in each of those two parentheses. I just didn't catch that until just now. So the probability that p-hat is less than 0.25. Less than, well, that's here on my distribution, right over there. And that's one that I'm just going to look up and get the answer right from the table and not have to do any subtracting or anything like that. So what we need to do now is compute our z-score so we can look it up on the table. So z equals 0.25, that's our x, or our p-hat, minus the mean, mu, 0.29, divided by the standard deviation, which is 0.02. Type that guy into your calculator, and you get a z-score of -2. So the probability that p-hat is less than 0.25 is the same as the probability that z is less than -2, which I can look up on my table pretty quickly. That is 0.0228. And by the way, that -2 would be -2.00, looking it up on the table, so don't go anywhere else. Just 2 and then over to the first one, -2 and then over to the first one. So we get a z-score of 0.0228, excuse me, and we can interpret that as a percent pretty quickly, so that would be 2.28%. Let's go back up and just see how that question was worded again. Would it be unusual for a random sample of 500 adults to result in 125 or fewer who do not have one? And since our answer down here is 2.28%, yes, it would be unusual. It would be, there we go. Okay, so that answers that question almost in its entirety. We just kind of skipped C for the sake of time. Thank you for listening. That's the end of the section. Get to work on the homework and let me know if you have questions. Bye.